accretion disk with jets. Now, that's sort of common with astronomical objects where you have these jets coming off of there where you've got a lot of material going in, but it's also going out. What's the physics of that like? In other words, what creates those jets, those sort of, I don't know if it'd be relativistic in this case, but in some cases it is. What causes that?
Yeah, that's, again, a very good question. And it's an active field of research, how these jets are being launched, where they are being launched from, what are the physical mechanisms that are involved in the launching mechanism, how and to what extent are magnetic fields, for example, connected to the launching of jets. So it's quite complicated, and again, it's an active field of research. So we don't really have a full and clear picture of how this works, but we do know that it's a combination of the conservation of energy and angular momentum of the rotating disk material that falls onto the rotating star. And as a consequence of these conservation laws, we have matter that is being expelled from the star. Now, you also pointed out correctly that this is a phenomenon that we see across a range of different scales and a range of different astrophysical objects. Think about the beautiful images of supermassive black holes at the center of massive galaxies that we have observed that also launch jets, or low mass stars of the mass comparable to our own sun, for example, as they form. They also have accretion disks and launch jets. So really on a variety of different size and mass scales, accretion physics seems to be ubiquitous.
And it's amazing. So let's compare this to the ultimate accretion disk, that of a black hole, which everybody's very familiar with in pop culture movies like Interstellar and all that. You see this very active region of infalling material spiraling in and releasing radio and X-rays and everything else. But this is a star, and this star is young but huge. Is there a difference between the accretion disk here around a star and what you would find around a black hole?
Again, excellent question. So there will be some differences simply because the central object is different. So as I mentioned earlier, this is a massive star. It's moving towards the main sequence. So it's already radiating. It already presumably has some form of stellar wind. And therefore, these outputs from the star itself will have an impact on the disk, on the disk structure, on the temperature of the disk, and so on and so forth, but also on the size and on the lifetime of the disk. There are, however, studies that show that the underlying physics of the accretion disk itself are independent of mass, and they're independent of the type of astrophysical source that sits at the middle, that is doing the accretion part. And that is incredibly interesting because it gives us really enormous power to study accretion physics in a variety of different objects. So there are some similarities, the underlying physics, but then there are some differences clearly just because of the environmental conditions that the central source creates in its surroundings, for sure.